So I can't do the matrix booklet because it doesn't really have any step questions in it, and I don't really want to do a bunch of random questions. So this is the 2019 step 3 question about matrices, and I'll go through all of the exam questions that they've asked since 2019, which is when matrices were put on the step course. So yeah, we have a matrix A. So this is part 1. Part 3 is actually by far the easiest part of this entire question because it's actually just pretty standard A-level maths, whereas A-level further maths, I should say, whereas this is a little bit different. We need to be aware that this is not talking about an invariant line. It's not talking about, a line by which a point gets sent to another point somewhere on the line, which is what A-level math, further maths talks about a fair bit. This is talking about a line of points which all stay where they are, right? So like 5, if your line is y equals x, 5, 5 stays where it is from this matrix, and then 6, 6 stays where it is, and 7, 7, and so on. So it is something slightly different, which is why these first two parts are probably a little bit less familiar than this last one. But yeah, let's get into it. So in some ways it's easier because you just need to send xy to xy, like not to some other point on the line. It's just xy goes to xy. So reading along the top bits, we have ax plus by equals x. So this is the line that describes where x would have to be in order to go to itself. And then this is the line that describes where all of the y's would have to be in order to get mapped to themselves. And now we need to show this thing here. Well, we kind of try and look at this as carefully as we can. Got an xy term, so it's tempting to maybe just times these together. But we've also got these a minus 1, d minus 1 terms before any kind of this xy comes along. So if we move this x over and this y over, that can give us the a minus 1 and the d minus 1 terms, right? If we just rearrange that like this. And now I'm thinking, well, okay, we could times these together, but again, we'd get these sort of x squared and y squared cross terms. That doesn't seem that good. We would get xy terms. Maybe there's a way to make it work from there. But actually, what we can do here is we can actually just rearrange this one for y, just taking away this and then dividing by b, um, and then just shoving that result into here. And you actually get there pretty quickly, right? Times everything up by b. And then you could just times everything by y just to really try and make it look like this, and we'll end up with and by minus 1, I guess I also times it by, and then we can factorize out, and we'll be done. So just a little bit of manipulation. It's just a case of step questions. You've got loads of time, so just try a load of stuff until you eventually get here, and you'll be fine. Show further this thing. Well, we have this thing, right? This thing times xy is 0. So okay, well either this thing is 0, which is fine, which rearranges, of course, to this. That would be great. Or xy is 0. Now, we can actually go up a couple of lines to the line that didn't even have y in it, because that eliminates the idea from y. Right, we can just, we can factorize out x from this thing here, and that just gives us this times x is 0. So either this is 0, as we wanted, or x is 0. So let's just think about what happens if x is 0. We go back to our initial lines. If x is 0, then by is 0. And for that to be true for all y, then b would have to be 0. And we also have dy as y from here. And for that to be true for all values of y, then d would have to be 1. But okay, if d is 0 and if b is 0 and d is 1, if you look up here, that term makes 0, this whole thing makes 0, and this whole thing is 0 anyway. And so either, back on this line, either this bracket is 0, which leads straight to this, or x is 0, which leads to this anyway. So we'll say that this is definitely true. What can we say about A if L1 does not pass through the origin? So okay, in that case, we have a line like this. There's actually a few cases for lines that don't pass through the origin. Either a line like this where E is not 0. I'm using E because we've already used C. And then I'm going to go through the alphabet. Either y equals f, where f is not 0. This is a horizontal line if f is not 0. Well, it's a horizontal line anyway, but where f is not 0, so it doesn't go through the origin. Or a vertical line, again, where g isn't 0, so it doesn't go through the origin. We just need to think about each one separately. So in the first case, again, we're mapping points to themselves. So x and then mx plus e gets mapped to x, mx plus e. So for x to be mapped to itself, this needs to be true. And for the y-coordinate, which is mx plus e, to be mapped to itself, this needs to be true. We can actually just read from this that, again, for this to be true for all x, we just need, because it's an identity now, we need a plus bm to equal 1, and we need be to equal 0. Now, e is not allowed to be 0 because this doesn't go through the origin, apparently. So that means b has to be. And if b is 0, then this goes away and a has to be 1. And then we can do a very similar thing down here, exactly the same idea, um, because again, E isn't allowed to be 0 here, so D has to be 1, which then makes C have to equal 0. Sorry, this should be a 0. Just a mistype, but that should be a 0. And this is the identity matrix, right? 1, 0, 0, 1 is the identity matrix. So therefore, A is the identity in this case. If we're in the second case, Y equals F, then we have a line that's going through XF and going to XF, where F is some non-zero constant. We multiply those two things out, I guess, to find the two rules. And again, just from this line, if this is true for all x, which it needs to be, then that makes C 0 and D 1, because again, F isn't allowed to be 0. And then you read up here and you get the same sort of thing. And again, you get the identity. And then finally, for x equals G, it's almost identical, right? Of course. And so we end up with the identity again. So in any case, A must be the identity if the line doesn't pass through the origin. Good. Part two, probably the most fiddly part of this, I guess. So considering cases B doesn't equal 0 and B 0, show if this thing here is true, then we have a line of invariant points. Again, not an invariant line, a line of invariant points, just like in part one. Okay, so if B is 0, we may as well start here. If B is 0, let's start on the probably easier case. If B equals 0, show this thing here. So let's put B as 0 in. And into here because we know because it says if this, then we know we can start here. So if we put B as 0 and we get this, which means either A is 0 is 1 or D is 1. So okay, let's now go further. Let's say okay, let's assume A is the one that's 1 and B is 0 here, of course. Multiply these two things out. Now x is equal to x is good because that's what we want. We want x to be mapped to itself every time. Now for the y's to map to themselves, we need this to be true. But of course, we can just rearrange this if we want to. This is a line. This is just the line that this needs to live on. This is the line. As long as C and D satisfy, or for any C and D, I should say, for any C and D, this is just the line that Y is mapped to itself on. And because X is always mapped to itself, this is fine. This is just what we're gonna. This is just going to be the answer. So this is the line that we've identified here. Is just going to be that. If D is the one that's 1, then we can do the same thing basically. It ends up being a tiny bit different. We end up with these two cases. So for x to always be mapped to itself, A would have to be 1, or x would always have to be 0. So the line x equals 0 is, I guess, okay for that. And if x is 0, then y is just y, which means it works for all y. So x equals 0 is a line that comes out from this. If A equals 1, then I think we are just going to end up with 1, 0, and then C would have to be 0 to make the x's go away. So it would just be the identity matrix as we had in the first part. So the only interesting thing here is the line x equals 0, which arises from there. Okay, so then we deal with B as not 0, which means we just have a more general matrix like this doing this. So then we come up with our two lines here. And now I've said it a few times, but this is the line that is described that has to that is the case when x is mapping to itself, I guess. So I've multiplied and then rearranged straight away. And this is the line that is the case if y is mapping to itself. Now, if x and y are both mapping to themselves, which they need to be, then these two lines need to be the same, right? Like it's no good if x maps to itself on the line y equals 3x plus 5, but then y maps to itself as long as you're on y equals 2x plus 2, because then the only case in which they would map to themselves, they would both map to themselves, is the intersection of those two lines. We need these lines to be the same line for both of these things to be doing this all of the time. So we just need to essentially show that this is the same as this. So what we can do is we can times this, and again, we've got this if condition, right? We need to force this if condition in here as well. So if we times this by d minus 1, that forces this if condition in, right? Because we've got a minus 1 times d minus 1. So that's just going to be bc. So we can replace that with bc. And now b is not 0, so we can divide by b, and we end up with the other line we were looking at in the first place. So if this is true, then this line and this line are the same, and this is fantastic. We've now got an invariant line of points. Maybe I said invariant line by mistake a few times there. We've got an invariant line of points. I've said a few times that that's what we're dealing with, but I probably misspoke a couple of times. But anyway, we're now here, so that's good. So this or this, you could describe it as, we've said the same thing already, so that's fine, is the line that arises. Part three, like I said at the top, is actually the easiest part of this question because we are actually dealing with invariant lines, which further maths discusses, right? The way that you set this up is like this, where you have a line, what mx plus k they've given me, which goes to some other point on the line, which we can describe as big X, m big X plus k. And then we can just multiply this out, which makes this. And if you replace or substitute this big X into here, again, this needs to be true for all X, which means it's just an identity. So when we expand out, we can just compare coefficients to give us this equation and this equation, this one for the x's and this one without the x's. It needs to be true for all values of x's, so this is perfectly okay for me to do. Rearrange this for m after a little while, and then shove this m into there, because you notice the thing that I'm trying to get to doesn't have any m's in it. So that's why we should be getting rid of them. So put the m's into here, and you end up with this, times everything by b, and then you can move these every term with a d minus 1 over and factorize out the d minus 1, and everything cancels pretty quickly, and we end up with the thing that we were trying to get to here. And I think we're pretty much done. So yeah, that's that question done and dusted. Thanks for watching.